Hi, in this module I'm going to talk about selection sort. Selection sort is one of the most common techniques to sort, to organize, to alphabetize values in a given collection. We're going to see how simple it is, and at the end of the technique I'm going to do some basic analysis about time performance. There are two basic steps on the selection sort. The first one is to find the largest value, actually to find the index of the largest value, and the second step is to swap that value, once we know its index, with the value in the last position or rightmost position. And then we need to repeat these two steps until all the values are sorted. So on the screen we have 5 numbers. Keep in mind that this technique is applied when we have a very large numbers of items. I'm using only 5, but you should think in terms of tens of thousands, hundreds of thousands numbers that needed to be sorted. Given these 5 numbers, the first step is to find the largest value. Well, the largest value is 37. Second step is to swap that value that we just found with the value in the rightmost position, which happens to be 13. So we're talking about swapping the position of these two values. So the other values stay the way they are. So 29, 10, and 14 do not change value, but 37 and 13 are going to swap their positions. So notice that once I finish the first 2 steps, I have one value, which is the largest value, 37, in the correct position, which is the last position of these 5 numbers. Now I need to repeat the same technique, the same 2 steps, for the other 4 values that are not sorted. So let me do that. So again, the first step is to find the largest value, which is 29, and then I'm going to swap that with the value in the rightmost position, which happens to be 13. So that will give me the following. That will give me 13, because I'm swapping that with 29. 10 and 14 do not change position, and now I put 29 because I swapped that with 13. And obviously, from the previous iteration, I have 37. Again, after applying the steps, I have now 2 numbers in the correct position. Now I have to repeat the same process for the numbers which are not sorted. So let's do that one more time. I'm going to find the largest value, and the largest value that I have is 14. And then I'm going to swap it with the position, with the value in the last position. But we realize that 14 is already in the last position, so there is no need to swap. We have applied the algorithms 3 times. We have 3 numbers in the correct position. So for the last 2, we're going to find the largest number, which is 13, is out of position, so we're going to swap it with the one in the last position, which happens to be 10. And that gives us 10 and 13, which we just swap, and then 14, 29, and 37 from the previous iterations. And at this point, as you can see, we have the numbers sorted in increasing order. So that's selection sort, a very simple process. Now, let's do some basic analysis. So first, finding the largest value in any collection is depending or directly proportional to its size. It makes sense. The larger the numbers of values, the larger it's going to take to find the largest value or the max value in the collection. So the step number 1, which is finding the largest value, we said that has an expected running time of ON. Don't worry now about what this ON means. It's simply terminology. The only thing we need to understand now is that this means that the task that we're performing, in this case, finding the largest value, is directly proportional to n. As the size grows, n grows, the amount of time taken to find the largest value will increase. Now, we understand that we need to repeat step 1 and 2, find the largest and swap, to place the values in the right position, to sort them. So we need to apply this algorithm, this series of steps, n-1 times, to be able to sort all the values. So we have something that takes place in n-9 times and something that takes place in n time or is proportional to n. Therefore, the expected running time for this algorithm we said is n squared. This is why selection sort is known as a quadratic sort, because the expected running time of this algorithm is proportional to n to the power of 2, n squared. Now, let's do something else. Let's try some different set of numbers. For example, 20, 32, 45, 49, and 61. So, first step, find the largest value, 61. Oh, that happens to be in the last position, so no need to swap. Okay, next step, 49, happens to be in the last position, no need to swap. 45, we realize it's also the largest value in the correct position, 32 is in the correct position, and 20 is in the correct position. In other words, the numbers that were given to us were already sorted. Remember that when we're given a problem, we do not necessarily know the state of the data. We don't know if the data is already sorted, if it's in the opposite order, or if it's in random order. So it could be the case that in this example, the values are already sorted. The algorithm will work, it will perform the same two steps that we just discussed. So when we do the analysis for the performance, it will be the same. So even when we don't have to swap any values because the values are already sorted, the expected running time for this sort still is n squared.